Hello everyone, in this video we are going to learn about binary trees. I will give you some definitions, different type of binary trees. We will discuss about some properties, prove some theorems about binary trees, and we will also discuss about some applications. We know that trees in general can have arbitrary number of children in each node. But this property is not necessarily required in many applications. In fact, there are a lot of applications in computer science that we can restrict the number of children for each node to only 2. That's why we are going to focus on binary trees, like the expression trees that can represent algebraic expressions, or phylogenetic trees, or for example in many lossless encoding algorithms we use binary trees. There are plenty of applications for binary trees. That's why we are going to focus on binary tree and discuss about them here. So a binary tree will be a tree that with this restriction that each node can have at most 2 children. Each child is either empty or another binary tree. This restriction allows us to just call the children left and right. Remember in the tree structures we actually defined a linked list to keep track of the number of children in each node, because we didn't know that how many children each node is going to have. But here we are going to have at most 2 child, so we just give them a name, left child and right child. So we will also refer to that left child and right child a left subtree and a right subtree. So by the subtree we mean if you have this node, its left subtree is going to be the set of all of descendant of its left child, and the right subtree is going to be the set of all the descendant of its right child. So we can have binary trees in very different forms. For example, if I have 5 nodes and I wanted to create a binary tree, there are many different ways to create a binary tree with 5 nodes. Here I'm showing a couple of them. For example, here you had, in all of them I am marking the root as in red. So you can see that all of these trees are binary. As you can see in each node, if you check, there are at most 2 children. For example, here there are 1, this one has 1 child, this one has 2, or for example here this one has 1 child, this one has 1 child, and these are all leaf nodes. Or for example here the root node has 1 child. All of the nodes have exactly 1 child. So based on the way that we actually put the nodes, you can create trees in different forms. And one more interesting thing about the shape of different binary tree is that it can actually causes very different height for the tree. For example, for this case, you can see that the height of this tree is going to be 2. Remember what was the height? The height for each node will be defined as the longest path from that node to a leaf node. And the height of the tree is going to be the height of the root node. So if I'm going to calculate the height in this tree, I'm just doing it as a practice to remember. We have discussed this in the previous video. So the height of the leaf nodes are going to be 0, right? All these leaf nodes are going to have height 0, and the height of this node is going to be the longest path to a leaf node, right? Or you can actually recursively define it as whatever is the height of its right child and left child, the maximum of that plus 1. So the height of this node is going to be 1, and the height of root node is going to be the maximum of height of its children, 1 and 0. It's going to be 1 plus 1. The height of the tree is going to be 2, right? Unlike that tree that gives you the height 2, let's calculate the height of the tree in this case. I have one leaf node, the height is going to be 0 here, 1, 2, 3, and 4. So you can see that the height of the tree in this case is 4, unlike I can get a height of 2 as well with exactly the same number of nodes. I'm using 5 nodes and it is giving me different heights. So here are different examples that in this case, again, the height of the tree is 2. In this case, again, in this case, the height of the tree is going to be 3, right? The height of the tree here is going to be 3. The height of the tree here, again, is going to be 3. So now you can see that if, why I'm emphasizing on the height, because we will see that in many methods that we define over binary trees, the time complexity will be depending on the height. So if we get a binary tree in a form that the height is higher, the time complexity is going to be higher. So we are going to actually like the binary trees that has, lower height, like this one. So try to actually think about what is going to be the maximum height of a tree with, for example, if you are going to have 6 nodes, or if you are going to use 7 nodes. With different examples, try to create binary trees in different shape and calculate the height for them. As you can see in this case that the height is the maximum height with 5 nodes. Actually, the tree is going to form like a linked list for you. From this node, you are going to just have access to one other node. From here, you are going to have just one other child. From here, you are going to have just one more child. From here, you are going to have one more child here, right? So none of the nodes actually have 2 child, and this makes it the longest height. So let's continue and see more definitions in binary trees. We will call a node a full node if the node has both left and right subtrees. So in this example, I have marked the full nodes in black. As you can see in all of these cases, the node has both its children left and right. And the leaf nodes that doesn't have any child are marked in green, and the rest of the nodes, which we don't actually have any name for them, are blue. Like this one or this one, that they only have one of the children either left or right. We also are going to define empty node or null subtree. So here you can see that in all of these nodes, I have actually shown them using just the dashed lines. And why we are defining empty nodes? Because we are going to focus on the programming side. We are thinking about trees in the context of computer science. So if I'm creating a reference to a node or a reference to a tree which is null, which we haven't created any node, we haven't created any tree yet, so we call it the empty node or empty or a null subtree. It basically for us shows that where we can add a node. It's just like a reference which is null, if you wanted to think about it that way. So now I can actually give you a recursive definition for binary trees. This recursive definition has a base and has a recursive part. So this is the base of the recursion that tells me that a tree of height 0, so we know that if a tree has height 0, it means that it is only a single node. So a single node is going to be a binary tree. A tree of height 0 is a binary tree. And the recursive part of the definition is telling me that a tree of height h greater than 0 is going to be a binary tree if it has at most 2 subtrees or 2 children, and each of those children should be a binary tree as well. So this part actually makes it a recursive definition, and this part makes it sure that it is going to be a binary tree, that all the nodes are going to have at most 2 children. So based on this definition, I can also add one more base to the recursion that tells me that an empty tree is going to be a valid binary tree, and it is going to be, because we have actually defined if h is equal to 0, it is a leaf node. When we have an empty tree, it means that the tree doesn't even have the root node. The empty tree doesn't have any node, right? So it's just like if you think about it in terms of, in computer science, it's just like you have created a reference to a tree that we haven't created that even a root node in that tree. So it's just like you have created a list which you don't have a linked list that you don't have even one value in that list, right? So even the root node is going to refer to null. We will define the height for an empty tree to be -1, although it doesn't have any nodes, so it is just a convention that we define the height for a binary tree as a -1. You will see that it will help us a lot when we are writing code. So another definition, we will call a full binary tree. We will call a binary tree to be a full binary tree if all of the nodes in the tree is either a full node or a leaf node. So if I actually showed you the previous example, if we don't have any node like the blue nodes here, that all the nodes are either a full node that has exactly 2 children, or they are leaf node, like this example. As you can see, all of the nodes are going to be either a full node, all the internal nodes are full, and all the rest are going to be the leaf nodes, right? And there are some very interesting applications for full binary trees, like in expression trees. If we have all the operators to be binary operator, the expression tree is going to be a full binary tree. Or if you know about the Huffman encoding is a very famous encoding algorithm, one of the very first encoding algorithms that it actually represents the data in a form of a binary tree, which is a which is a full binary tree. So now I'm going to actually talk about the implementation a little bit. In this video, I'm not going to show you the complete code, but just a brief description. So we have discussed about the implementation of trees. Remembered we had a class for node and a class for the tree. Here we are going to do exactly the same. We are going to have a class for node that I'm going to call it binary node, and another class for binary tree. So let's focus on the class for binary node. The class for binary node is going to be very similar for the class of node that we defined for linked list. Here I have a field that keeps the actually the data that I wanted to store in the node. You can see that the type of the element is any type. This is a generic implementation. And unlike the previous implementation of tree, that I have created a list of references to actually refer to the children, I'm going to actually work on a binary tree, right? There are going to be at most 2 children. So even if both of them are going to be set to null, that's fine. It's going to be much easier that instead of showing it as a list, show it using 2 references. So it's just like you have a node very similar to the node implementation in singly linked list. And in the singly linked list, you just have one reference that refer to the next, remember? Which actually refer to the next node in the linked list here. Each node are going to have, it's just like it has 2 references, one for the left and the other one for the right node. You can see that these references can be null. If it is null, it means that they're okay. If both of them are null, this is going to be a leaf node. If one of them, each of these references can be set to null. And here is a constructor that I have written for the binary node. You can actually add more constructor. If you want, the full implementation is available on Blackboard. And we will actually go through it during the class. So in this constructor, it's given to you some element and some left and right references that you will set to the left and right reference, left and right subtrees. I can define different methods in the binary node to actually for the set and get. And this is the implementation for the binary tree. So in the binary tree, the only field that I keep is going to be a reference to the root node, remember? So it's going to be a binary tree, right? And you only need to keep the reference to the root. Then from the root, you can access to all other nodes. I have defined 2 constructors here. One constructor that will create an empty binary tree. You can see that even the root node has been set to null. So when you use this constructor, you will create a binary tree, an object of a binary tree, of type binary tree. But it is empty. It doesn't even have the root node. But this one is going to create a binary tree that exactly has one node, which is going to be the root. So like this. But the root doesn't have left or right. So you can see that these 2 constructors are not enough to actually create binary trees with more than one node, right? Using the first constructor, I can create a binary tree with no node, and using the second constructor, I can create a binary tree with just exactly one node. So here I need more methods to make sure that I create bigger trees. The tree can actually grow. But how I'm going to write those methods? Let's go back to that recursive definition that we defined. Remember, we had this recursive definition for the binary trees. The base case of that tells me a tree of height 0, a single node is going to be a binary tree. And the recursive part, if I follow actually the recursive part, I can create bigger trees. Just using these 2 definitions, I can create bigger trees. And now you can see that why I have defined this. I have added one more base case, this empty tree as a binary tree as well. If I wanted to actually compare these 2, you can see that this, let's actually give them some name. Let's use a different color here. So let's just use this one, call this one base. Let's call this one base 1, which is actually telling me that an empty tree is a binary tree. if I'm going to show you in the definitions, in fact, this is going to be base 1. This constructor is going to create a binary tree which is an empty binary tree. This is exactly representing base 1 here, right? And base 2, this is going to create a binary tree with just one node, which is going to be the root node. So if I'm going to show you, this is going to be base 2. So I need one more method that actually follow the recursive part, and using this one I can create larger binary. So the part that will help us to create larger trees is going to be a method that we call it merge. And what is the purpose of this method? This method will actually takes two other trees, two shorter trees, to a smaller trees, and merge them, create a larger one. For example, if I have a tree like this one, and I have another tree like this one, I can take these two trees, let's just call this one T1 and T2, right? Add another node, set T1 as the left subtree, T2 as the right subtree, and create a larger tree. So this one, let's just call this one T3. So it's going to be a larger tree, right? This is exactly what I am going to implement using this method merge. The argument, there is going to be two subtrees, T1 and T2. As you can see, both of them are some object of type binary tree. And I'm also passing some data as the value of the root node. Remember, I just explained that whatever is T1 and whatever is T2, T1, T2, you are going to add one more node, and this root item is going to be that value that I'm going to keep in the root node. So let me just clean up here a little bit. So here, this sanity check is just checking that the root node of T1 and T2 are not the same. If it is the case, you are going to create something, something like this, that T1 and T2, both of them are referring to the same T1 and T2. So if it is the case and you passed one tree, it's just like you are passing one tree, and you wanted to actually merge them. So you are going to create a situation like this. And this is not good, right? You don't want to have a tree, a tree like this. This is not going to be a tree. From the root node, the both left and right subtree are referring to the same thing. So this sanity check is just avoiding that. It's just checking that if T1 dot root is equal to T2 dot root, it's going to be an error. The last part of it is just checking that they are not equal to null. If both T1 and T2 are null, so that's fine. You are going to actually create a root node that both the left and right subtree of it are null, and this is fine, right? The last part is just checking that if it is equal to null, it doesn't matter, let it go. But if they are not equal to null and they are equal to each other, we don't want to create such a tree. So after checking that sanity check, the only thing that we need to do is we need to create that root node, right? I have this T1 and I have this T2. Like, for example, whatever. I'm just actually making some example. It doesn't matter that, it doesn't mean that T1 or T2 are like this. So T1, this was T1 and this is T2. I need to create another node, put the whatever is the root item inside that, right? And also set these references. So this is going to be done using this constructor. This is a constructor from the binary node, right? I'm creating a node, put some value inside that node, and set the left and right subtree to be t1.root and t2.root. So this is going to be the value of this is going to be the new root. The last part is just checking that after I am actually merging T1 and T2, I don't like to actually T1 and T2 have access to these nodes. Okay, these nodes now are going to be a part of this larger tree, right? So T1 and T2 from outside, they shouldn't have access to the nodes. It's just, it will, after they are merged to this new node, T1.root is going to be set to null and T2.root is going to be set to null. So those references, those trees from outside are not going to have access to this node anymore. Here, in this part, it's just checking that if you are calling the merge over T1 or you are calling the merge over T2, you are not going to actually change the T1.root to null or T2.root to null. So now let me actually show you that how we can actually use these three methods, those two constructor that we had here. Remember this constructor that was the first, that base 1, and this constructor which was base 2. Using these two constructor and the merge method, how can we create different kind of binary trees? For example, like this one. I'm going to show you that how it is possible. So let's start with simpler example. Like let me add a slide here. Let's just, okay, let's just, instead of actually working on this one, I'm going to work on something simpler, like a binary tree in this shape, that this is, for example, 1, this is 2. How can I create a binary tree like this? I know that the constructor, the first constructor, is going to give me a null binary tree, and the second constructor is going to give me a binary tree with exactly one node, and I also have them merge. So I can create a tree which only have one node and the value of that is 2. So let's create, for example, T1 to be using the first constructor, new binary tree, and pass the value 2. Okay, and let's create another tree which is going to be an empty binary tree. So it's just like, I'm going to show it to you using this, but it's basically know that this is going to be a null binary tree. So let's call T2 to be an empty binary tree. Let me just move this. So as you can see, this one is going, the first one is going to call this constructor, right, that passed some value, and the second one was actually calling this constructor. So using this one, it's just like I have created a tree that this is the root of that, and let's actually just have probably use a different color. I'm going to actually make a difference between the nodes and the tree structure. This is going to be T1, right? And T2 is something like this, that the root is actually referring to null. Okay, so now I can use the merge and create a larger binary tree that T2 is going to be the right subtree of that and T1 is going to be the left subtree of that. This is going to do something like this, that a new tree in this form would be created. And I'm going to actually put 1 inside that. So it's just like I can, in fact, create another tree, new binary tree, and I can actually just create it as an empty binary tree. This one, this T3 is also going to be empty. But then I will call merge. As you can see, merge in fact has been defined as a method in the binary tree class. You can actually check it out in the code of your binary tree available on Blackboard. Merge over T3, I'm going to call merge and then pass what is the value of the root. I wanted 1 to be the value in the root. And what is the first subtree? The left subtree is going to be 2. So the left subtree is going to be T1. The right subtree is going to be T2. What this method is that so in that T3 that you have, root is null first, but then you will actually just create a node. You put 1 inside the node and you also set the reference of T1 will be set as the left subtree, and the reference of T2, sorry, the root of T2, which is null, is going to be set as the right subtree of T3, of the root node. That's it. Now I have a tree in this form, which the root node is 1 and the left subtree is 2 and the right subtree is null. Let me actually show you one more example. Now assume that I'm going to create a tree like this. Let's see. That this is going to be 1, 2, 3, and 4. Right? So how to create a tree like this? I'm going to start it. As you can see, we should start it from the base cases. We should start it from it's just like we are creating it a bottom up way from the leaf nodes and then get a larger one. So the first thing that I need to create is I'm going to create a tree that has exactly 1 node, and that node is going to have the value 3. Let's just call that one T3. I'm going to just follow the same kind of naming. So new binary tree with a value 3. So it's going to actually create a tree for me that has 1 node, and that node is going to have 3. Let's create another node. I'm going to call it T4. New binary tree and with value 4. Remember that all of these binary cases, constructor are actually this second constructor. This is the constructor that I'm using. It's going to create another tree with exactly one node, and the value of that is going to be 4. Now I'm going to, in fact, create this part, a tree like this. How I am going to create a tree that let's call it T2. I will first create an empty binary tree, so I'm passing nothing to that, and then using merge over T2, passing the value of 2, so the root is going to have the value 2, and also passing T3 as the left child, T4 as the right child. So you can see that this one is going to create a tree like this. It's going to actually have the 2 as the root. Whatever you actually have created here is going to be set as the right subtree, left subtree, and this one is going to actually be as the right subtree. Now I'm going to actually create the larger tree. As you can see, the right subtree of 1 is in fact null. So to be able to actually merge this one with null, I need to actually create an empty tree as well. Let me call it temp. I'm going to create an empty binary tree. So I'm not passing it null. So this is the one actually that's going to represent the right subtree of 1. And I'm going to create T1 as well. This is at first an empty tree. Then I will call merge over this one. Pass T2 as the, pass, what is the value of the root? 1, right? And then I'm going to pass T2 as the right subtree and temp as the left subtree. So now this T1 is going to exactly be the tree that I wanted to have. That the left subtree of that is going to be another tree like this one, and the right subtree is null. So following exactly the same actual logic, you can create a binary tree for this shape, a binary tree in this shape. How this is actually in fact the full set of lines that I need to execute to create that kind of tree. In this case, you would actually create a tree that with one node, which the value of that is 1. This line will create another tree with exactly one node, that the value of that node is going to be 5. This one is going to create a one node that the value of that is 6. T1, T2, and T3, all of them are going to be some empty trees. And then here it's actually, I've actually put the merge at the end. So T2 will merge T4 and T5. So T2 will be something like this. 4 and 5, right? I'm passing whatever is that T4 is this node, and passing T5 as the right subtree. Okay, so T2 is going to have a root node with value 2, and the right subtree is going to be then this tree, and the left subtree is going to be this tree. And then this part T3 will be a new tree with the root node value 3, and the left subtree of that is going to be T6, right? And the right subtree of that is going to be temp, which is an empty tree, right? So it's just like this is in fact null. We are not representing anything there. So let me actually, in fact, it's better to clean it. And then the last part is, okay, I have one T1, the root node value is 1, the left subtree is T2, the right subtree is T3. Okay, so this is exactly that shape that I was looking for. So your lab is going to actually play with these three methods, merge and those two constructor, and create a different shape of trees. One part of actually the lab is for you to think about binary trees with different number of nodes. For example, if I have 7 number of nodes, what will be the shape of tree with maximum height? What will be the shape of the tree with minimum height? When you come up with the correct form of it, then you can create the tree using the constructor by just calling the constructor and then merge. So that's going to be your lab for this week. So in addition to these methods, you can add more methods for your binary tree class. Never forget that whatever we discuss here is going to be some collection, right? You are going to create a collection in a form of a tree. So this collection are going to keep some data. All of those data are going to be stored in the nodes in a form of a tree. So sometimes I wanted to actually clear all the data, remove all the nodes. If I'm going to remove everything from the tree, I don't need to remove those nodes one by one. I just need to set root to null. This is exactly like the linked list, that whenever you set head and tail to null, it's just like you would create your whole linked list empty. So whenever I set root to null, the whole tree will be set to null. The whole tree will be empty, in fact. Checking that if the tree is empty or not can be done by just comparing root to null. And if in case you need to give access to the root, you can have a method like getRoot as well. So some other methods which are going to be very useful in this case is, for example, I wanted to know how many nodes I have in my binary trees. I have created a binary tree, I have created and added some nodes, I have created a larger binary tree, but I don't know how many nodes are there. So I can define a method for calculating the size, how many nodes are in the binary tree. This actually function is going to be a recursive function, very similar to what we have discussed for trees. In general, there is going to be two functions. One helper function, this is going to be defined over the class binary tree. So this is the public method that we have defined over the class binary tree. So what it does, it in fact calls the method size which has been defined over the class binary node. It is just a different form of creating that method. How we are going to implement that recursive method? If you think about how many nodes you have in a binary tree, in fact, there is a simple recursion relation for that. So this is going to be your root, right? The number of nodes that you have in the in your binary tree is going to be all the nodes that you have in your left binary tree plus all the nodes that you have in your right binary tree plus 1 because of the root node, right? So this exactly gives me the recursive definition. Whatever is the number of nodes in the left subtree, whatever is the number of nodes in the right subtree, plus 1, it is going to be the number of nodes, right? So this is going to be something that I'm going to return. This is recursive because I'm actually calling the same method, and there is going to be a reference, right? When the node is null, there is nothing, in fact. If, for example, you have you are calling this method over a null, if the reference is null, I'm actually just trying to explain this, that if the reference is null, it means that there is no node, right? So it just returns 0. This is the base case. So similar to that, I can define the height for the binary tree as well. Again, there is going to be a helper function. This is the public method height that will define over the binary node, and there is going to be another recursive method height that has been defined over the class binary node. I'm calling it over the class binary node, and in fact over the root. What is the recursive definition of the height? So the height is the maximum length from the root node to any leaf node, right? So that leaf node is going to be either in the right subtree or in the left subtree. So whatever is the height of your left subtree and whatever is the height of your right subtree, you need to first know them, right? And whatever is going to be the maximum, that longest path is going to be through that one, right? So for example, here it is from the left side. So we can define the height to be this recursive definition, that the height of the maximum of height of left subtree and right subtree plus 1. And you can also define some base cases for the height, that the height of an empty node, remember the height of an empty tree is going to be -1, right? I can actually just use that base case here as well. This is exactly the recursive part, that I'm going to take the maximum between the height of left subtree and the height of right subtree plus 1. This is exactly the recursive part of it. And the base case is that if t is null, it's just like you don't have, there's nothing, right? So you return -1. So when you think about it, if you call this method height over a leaf node, it will call it over its left subtree and right subtree. Both of them are null. So both of them will return -1. The maximum of -1 and -1 is going to be -1 plus 1. The height of the leaf node will be 0. So now I'm going to actually go and talk about those three traversal methods that we have discussed about them last week in the previous video. Remember, we have talked about the pre-order, we have talked about the post-order. Pre-order was that if you have a tree like, let me actually just write down some example. 2, 3, 4, and this one 5, for example. The pre-order is going to just visit each node before visiting its children, right? So the pre-order of this tree is going to be 1, then you call it over the left child, then you call it over the right child. But this is recursive, so 1, 2 pre-orders, so 4, and then 3, and then 5. This is going to be the pre-order. The post-order is visiting the node after you have visited the left and right subtrees. So if I'm going to actually print the post-order for this tree, it is going to be post-order. So you have to visit the the child first. You have to visit the child first. There was no left child, so the first number that will be actually visited or printed is going to be 4. Then it will be 2. Then it will be 5. Then it will be 3. Then it will be 1, right? So this was the pre-order and post-order. Now we can actually define in order for binary trees as well. Because we are only going to have 2 children, the in order is going to have a meaning. So instead of visiting the node before the children or after the children, you can visit the node between the children. So first visit the left child, visit the node itself, and then visit the right child. So in this tree, be careful, let me actually just clean up a little bit. I'm going to rewrite exactly the same tree here. I just wanted to emphasize on the fact that what are the left and what are the right. 1, remember it was like this. 2, 3, and I think it was, I don't remember, oh my god. So it was 1, 2, 3, 4, and 5, right? So I just wanted to make sure that you know that the 4 is the right subtree of 2 and 5 was the left subtree of 5. So what is the in order in this case? The in order of this tree is going to be first visit the left child, then visit the right child. So from 1 you go to 2, from 2 you wanted to actually first visit the left child. There is no left child, so 2 will be visited. Then the right child, so 4 will be visited. Then the you go back to the root, so 1 will be visited, then the right. So at 3 you first need to visit the left child, which is 5, and 3, and there is no right child. So the in order traversal of this tree is going to be this one. This was the pre-order. 1, 2, 4, 3, 5, and this was the post order. 4, 2, 5, 3, and 1. So let's do it over another example. From 1, this is going to be larger. You first need to visit its left child. So from 2, there is no left child, so you visit the B first. And then from B, you visit its right child. From D, there is no left child, right? And then so you visit D, there is no right child for D, you go back to B. And then from B, you go back to A. Now it's time to visit A before visiting its right subtree. So from A, you visit C. From C, you first need to visit its left child. You first need to visit its left child. And there is no left child for G, right? So G will be visited. Then from G, you go back to E. You will visit E. Then you try to find a right subtree. There is no right subtree for E. You go back to C. Then it's time to visit C. Then from C, you go to its right subtree. From F, you need to first visit its left subtree. And from H, there is no left subtree, so H will be visited. And then you have no right subtree, you go back to its parent. Now F will be visited. From F, you then visit I, because there was no left or right subtree for I. Then you go back to F. Then you go back to C. Then you go back to A, and the whole recursive call will be finished. This is going to be the in order of this tree. in order traversal of the tree. And here is the complete in order of that. I think I got the correct one, right? So now let's have a look at the runtime for the binary trees. So far we have seen that for the linked list and arrays, the time complexity of almost all the methods for removing an item, adding an item, and everything was n. But when we are actually working on a tree, we will see that the shape of the tree is going to actually really matter on what we are doing. The tree can be actually growing one way and creating a very long tree, or actually growing very evenly and, for example, create a shorter tree like this. Basically, everything is going to, I shouldn't say everything, but most of the methods that, for example, you are going to remove an item, you are going to add an item, you are going to search for an item in your tree, it will depend on the height of the tree, the shape of the tree. So that's why it is important for us to discuss about the what is going to be the maximum height of the tree, what is going to be the minimum height of the tree, what is going to be the average case. In fact, the maximum height of the tree is going to be n-1. It is exactly this case that you grow the tree one way. If you actually think about it, if I have, for example, 5 nodes, the height of this tree is going to be 4 if you actually grow it just in one way. If you grow it very in a form of a balanced form, this is going to be log of n. And if I'm going to actually be more precise, this is going to be the scaling of log of n. This is going to be the best case for the minimum height of a tree with n nodes. The maximum height was n-1 and the minimum height was the floor of log of n. And if you just randomly create a binary tree, on average case, the height of the tree will be actually a square root of n if you don't actually care about how you are forming it and just randomly create a binary tree. So these are going to be the worst case, best case, and the average case. So in fact, I'm just going to emphasize on this fact that log of n is way better than n. And so if we can get a time complexity of log of n, we should definitely aim for that. So for example, if you have a large value like this, 1000 power n, if you get the log of this, you can see that it's going to be just 10n. Now compare these two values. This one is better or this one? So of course, log of n is way better than n. So we should be careful that if we can go get this best case, we should aim for this best case, not n. Just one thing before I actually just go forward and explain about the application, I wanted to take some time and go back and talk about the time complexity of the height and size. In these methods that we have discussed, for example, the method size, remember it actually calculated the number of nodes in the tree. When you call, for example, the size over the root node, it will call it over the left subtree, it will call it over the right subtree, right? So basically you are going to call it over all the nodes. You need to go through all the nodes to be able to count all the nodes. So the time complexity of this recursive method is going to be T of n. It doesn't matter what is the shape of the tree, the time complexity will be theta of n. The shape of the tree will actually change the memory usage, because if your tree is not balanced, the number of recursive calls that you are going to keep in the stack frame is going to depend on the height of the tree. So that's why it's going to actually affect the height, the memory complexity. The height is going to affect the memory complexity, but the height is not going to change the time complexity of this method. This method is going to run in O of n. This is exactly similar to the calculating the height. When you are calculating the height, you are going to call over the same function over the left subtree and the same function over the right subtree. So you are calling it over all the nodes. The time complexity is going to be theta n again. But the space complexity is going to be theta of h. Whatever is the height, that's going to be the maximum number of stack frames in the memory. So now you can actually think about the time complexity of pre-order, post-order, and in-order. The code for in-order is available in the, the complete code for in-order is available in the source code I posted on Blackboard. You can check that. The time complexity of all these methods are going to be linear because the intuition is that you have to visit all the nodes if you are, for example, going to print them, right? So the time complexity of all the tree traversals is going to be theta of n. Doesn't matter what is the shape of the tree. So now let's actually go back and talk about the applications of binary trees. One of the applications which is very interesting, expression trees. Remember when we talked about the stack, we have also talked about the expression tree. Any algebraic expression can be actually represented using a binary tree, where in this binary tree all the internal nodes are going to be some operator and all the leaf nodes are going to be some operand. For example, a complicated expression like this one can be represented using a tree like this. If I'm going to in fact read it and show you that which part is going to be represented by which part, this 4a is in fact this part of the tree. And then 4a plus this b plus c is going to be represented with this part of the tree. The full parenthesis here will be represented in this subtree. And then you can see that whatever is the result of this parenthesis will be multiplied to c. So it will create a larger tree, subtree here. Then these parts are actually simpler. 6 minus e is going to have this subtree. D divided by 5 is going to have this subtree. And you are going to actually add these two together and then add the result to, this part, whatever is this part, add the result to this part, which is going to be the full expression tree. A nice thing about expression trees is that after you have converted your algebraic expression to an expression tree, then the rest of the calculating the expression, converting it to post order, converting it to pre-order, all of it is going to be very easy. It's going to be just some traversal over the tree. For example, if you have the expression tree, if you traverse over the tree and print the post traversal, this is going to be the post order of the original expression. If you print the pre-order of the tree, pre-order traversal of the tree, it's going to be the pre-order of your first expression from the original expression. The in order traversal will give you the in order form of your original expression. This is very actually nice properties. And it's going to be very good exercise if you try to write down a program that, for example, you have created an expression tree, how to calculate the equivalent expression. Just assume that you have all the values, and you wanted to actually you need to just write down some tree traversal over this tree to be able to calculate the original expression.